All right, so let's go ahead and get back to optimization. This optim function is the one I like better. You can use it for multi-dimensional optimization, which is usually what I need. Notice the parameters are similar, or the arguments, I should say, are similar that you pass in. You have to provide initial values, which are, you can really start with kind of moment guesses or something like that. It can be pretty simple. Then you pass in the function to be optimized. You can have the gradient returned, or you can actually specify the gradient, I believe, on this one. And then you can use, there are different methods of optimization that you can use. You can also change the control, like the tolerance of the algorithm, the number of iterations you span, the criterions, and so forth. By default, the minimum is found, but the maximum, you just change your control parameter FN scale to, or FN scale to -1 using this kind of command. You have to put all your control parameters in a list object. That's typical for any R function, more or less. Here's an example. I'm not going to run through this because you've already kind of seen something like this done. But notice this is a two-dimensional function with a third variable for return. X gets submitted as a vector. Okay, so there's two components to x. Then the function gets defined and returned. You can plot it. Then here's the use of the optim function. So you can, here we're looking at the maximum points on the contour plot. If convergence is 0, then it means you've reached convergence. If convergence is 1, it means you reach the maximum number of iterations and never finalized. So notice the result is here, because you will have the 0 point between your function values between the range or domain of -2 and +2. You're going to reach convergence. If you do not specify a good range, then you will not. I'm going to skip this for time reasons. You can also do constrained optimization. I'll let you look more into this, but there's ideas for how to do this. Notice that you need to be a little bit more careful and look at the literature about what method to use for this. And you need to be very careful about constraining using inequality constraints in particular. Finally, adaptive rejective sampling. So the idea is here, sometimes you need to get values from a density function that is not in a nice closed form, or is difficult to compute, or computationally costly to compute. And so adaptive rejection sampling will generate a random sample from a distribution with a particular distribution, but it uses another density that's easy to sample from, and then uses this inequality to then estimate these f of x values on the left-hand side. The algorithm goes like this. You generate y from the easy to generate function, usually something just set in R, a D function within R. Then you generate a uniform random variable. If U is less than that ratio of F over C times G, then X is equal to Y. Okay, this makes sense because if this ratio here is greater than the uniform number, then we appropriately determined value C, a case where X is approximated by Y. You can only do this for univariate cases. If you take like a computational statistics class, I would think that, this would be a unit in the class. In fact, I, as a graduate student, wrote all my own code to do this kind of sampling algorithm, because I needed to do something much like this, not realizing that the functionality existed within R, although it may not have, because that was many years ago. Here's the ARS function, which will do your adaptive rejective sampling. Notice you just need to put in your sample size, your function that returns the log of the function, where U is the density that you're wanting to sample for, so your target density. F prime is going to be the partial derivative with respect to your parameter or your vector U. Okay, so actually when I wrote this, I had to work out and define an f and an f prime as functions. And you have to do the same thing here. It's just that this provides the algorithm, but you still have to define f and f prime as functions here. So here's an example. You can define a function, you can integrate it like we've done before. You can define the log density and the derivative of that log density, just like I talked about on the previous slide. So notice these are both defined as functions of your vector x or value x. And then you put these in, the f log and f log prime, to your ARS algorithm. So you don't have to write your own algorithm. You can define your functions appropriately and then create a sample size, in this case of 10,000 random samples.